Magnetic field is generally something that we can control. If I'm dealing with a solenoid, I know that the magnetic field is equal to mu n sub I, or mu naught n sub I, or n times I. That's the strength of the magnetic field coming from a solenoid. U sub naught is a constant. N depends upon the geometry, is the number of wires per length for a solenoid. I can control I. If I have a variable, if I have a potentiometer and I can vary the potential difference, in other words, vary the voltage, I can vary the amount of current. So B, I can control. The speed, I can easily check the speed. All I need is two sensors here, and when the charge goes by, this sensor, the sensor will pick up when the charge goes by. If I know the distance between them and I know when the sensors are set off, I can figure out how fast this thing is going. So I can measure V. So I shoot this particle into this magnetic field. I look to see how it curves, and I know that the radius of curvature is definitely connected to the mass divided by the charge. This is a relatively unique identifier. It doesn't work 100%, but it does narrow it down a great deal. The mass per charge ratio is relatively easy to find. So a proton has a mass, it's going to go to some memory. It was, let me do electron because I can do that one better. So for the electron, the mass over charge is 9.11 times 10 to the negative 31st, I believe, divided by 1.6 times 10 to the negative 19th. Doing magnitude at the moment, so let's just do magnitude. I'm going to bring in the negative in just a second. And so this is some number. If I'm dealing with a positron, mass to charge is going to be pretty much the same thing. There are some subtle differences there, but probably not for this type thing. So if I see something with a radius, because if I can control, I can control V to some extent, but I can definitely measure V, I can control B. I have this particle that has, so I can then predict, if it's an electron, I'm going to have a certain radius, or a positron will have basically the same radius of curvature. The big difference is the positron will curve this way, the electron will curve that way. So I can start identifying particles. And this was a huge step to being able to do this. Then the next step was, how do you actually see particles? How do you see an electron, or the parts of an electron? Enter Glaser in the 50s when he develops the cloud chamber.
Wouldn't you affect it when you observe it?
Not significantly not significantly. When you send it through a cloud chamber or a bubble chamber, it's the charge that will react with the environment. It's not like it's necessarily colliding into things. It's it's not the collisions that cause the track, it's the charge that does. The charge affects the things around it. So one of the reasons why this is of significance to me is my dissertation was in hydrogen physics. Now, we are more sophisticated than cloud chambers. Cloud chambers, you have a supersaturated environment, and when a charged particle goes through it, you see the small little, looks like a smoke trail. A couple of years ago, the teacher across the way actually built one, a cloud chamber. And then the next step was the bubble chamber, where we take superheated liquids where the slightest disturbance will cause bubbles, and then you can look at the bubbles. And then now it's electronics. You basically have a whole detector here, here, and here, and I know something went here, and then something went here. Except you got millions of these things going through, and then you use computers to recreate the most logical scenario. All right, so let's do some numbers. I have a proton going through magnetic field of 5 microtesla at a speed of 2 times 10 to the 7th meters per second. Magnitude of the force, well, plug and chug. I guess I do need to explicitly state going through and moving perpendicular to magnetic field. So it's 1.6 times 10 to the negative 19 coulombs times my speed, 2 times 10 to the 7th meters per second, times my magnetic field of 5 times 10 to the negative negative 6 Tesla. And we end up with a magnitude of force being go for 5 times 2 is 10, so it's 16. I got negative 25, 18, so 1.6 times 10 to the negative 17?
That's right.
Okay.
So when we calculate the force, we include the velocity, because in your derivation, you cancel out velocity.
That's what I was trying to find the radius here. That's what I said it equal to if we square it for r.
So the actual equation, it still holds F equals.
Yeah.
AV.
We're gonna adjust the force to the V states.
Okay.
Units?
Newton.
Absolutely. Which tells us that a Newton must be the same as a Coulomb meter Tesla per second. Which tells us that we can have a unit of time of a second is equal to a Coulomb meter Tesla per Newton. Fun with units. You have a new unit of time. Okay, it's a rehashing of an old unit of time, but a new way of expressing a second. Country music television for Newton. The acceleration, the centripetal acceleration of this proton, well, I know F equals ma. And so I got 1.6 times 10 to the negative 17th newtons is equal to the mass of a proton, which is 1.6 times 10 to the negative 27th.
Is it a proton?
Yeah.
1.67 times 10 to the negative 27.
Okay. Times a, so I can find the acceleration of it. It's gonna be something times 10 to the 9th. Around 9 times 10 to the 9th. 9.2.
9.58.
5.8 times 10 to the 9th.
Yep.
Meters per second squared. And then we can just keep going, figure out what the radius of curvature is.
So the there also components to, that acceleration? Like which direction is that acceleration going?
Yeah, I didn't actually specify. I would need to give you more information here for us to identify that. I know that this acceleration is perpendicular to the force. Oh, sorry,
Or in the direction of the force?
the acceleration, it's in the direction of the force, it's perpendicular to the direction of motion.
Okay.
So this is a centripetal acceleration.
Would you ask us to find centripetal acceleration? Or, I meant the other component of the acceleration?
Alright, so let's throw some directions into it. So let's change that speed into a velocity. 2 times 10 to the 7th meters per second I hat, and let's make B in the K hat direction. So we can find the direction of force now. We need to define a coordinate system here, and it is assumed a right-handed coordinate system. So let's go with I, J, and therefore K coming out of the board. So B is coming out of the board. My velocity is in that direction. It is a proton. So my force will be 1.6 times 10 to the negative 17 newtons. In which direction when it first enters?
J hat.
Why J hat?
Direction. And then the B is pointing this way.
Right hand roll.
It's down.
It's down. Yeah, it is somewhat awkward.
I'm not even left-handed.
It's the influence pressure. It will be down there. So when it first enters, the direction is in the negative J hat direction. It does start to curve, so it's only in the negative J hat direction in the immediate moment that it enters the magnetic field. Now, from a realistic point of view, can you actually have a barrier here? Can I have the magnetic field sort of trapped so that outside it doesn't feel it, and once it reaches some line here, it suddenly is in it? We can actually get pretty darn close at this point. So it is not unrealistic to use something like this. Sometime in the 60s was, this was considered to be sort of cutting edge at this point. We have enough technology that we can isolate the magnetic field pretty well. So so bringing direction into it would be something like that. And so the acceleration, when it first enters, would be in the negative J hat direction.
And if we were to find the centripetal, would it be in the direction of the magnetic field?
The centripetal acceleration would be perpendicular to it.
Okay.
Because the acceleration has to be in the direction of the net force, and the net force is perpendicular to those two, because of the cross product.
That makes sense.
The result of a cross product is always perpendicular to the original two vectors.
Okay.
Other questions?
What do they call that, orthogonality? I think.
That could very well be.
This cockpit.
Yeah. I think
think so.
they would always say that word. Like they would say the cross product, find a vector that's orthogonal to V and B. So you have to take a cross product.
Yeah, then that would make sense. I was trying to think of, I know if I've dealt with orthogonal within physics, but in terms of calculus speak, yeah, I haven't had formal calculus in quite a few decades.
That's understandable.
And then you get to physicists who they go, no, we'll just teach you the math you need to know and whatever bastardization of language they use. Stupid physicists, jerk faces.
But wouldn't some math techniques help to like make some different discoveries?
Oh yeah. Oh yeah, there's, one of the beginning courses that you take in grad school is mathematical physics, and it's just looking at math with an occasional concept.
That sounds fun.
It is. And then you start specializing, and you're going, wow, I never have to use that math again. Until some student starts asking you questions, and you're going, oh, wait a second, I know I solved this one. All right. So, charge, this is the charge that's flowing. So force is equal to Q times ds dt cross B. If I have a current flowing, I generally don't think about it in terms of a single charge, but I have some bit of charge here. And so this charge here represents, some portion of charge of a current that's flowing. So I'm just going to move dt over, and so I get Q over dt times ds cross B. So this Q over T dt here is just the actual current flow. I know typically we write the Q dt, I'm doing a little hand wave here. So that's just current. This ds is sort of the bit that is running through it's basically the length of the wire. And so the force on a current carrying wire. So this is force on current carrying wire. Of length L. I write that and then I'm thinking, well, really I should be putting more words on here, which is not my original intent. Just recognize this is the length of wire L that is going through the magnetic field. So if I got a wire this long, but my magnetic field only covers this much of it, all I care about is the part going through the magnetic field. So one current carrying wire of length L in B. That's clear. So I have some current I here. I got a magnetic field, of course, coming out of the board. Those are the dots. And let's go ahead and isolate. I got my magnetic field in this region right here. This is length L. Let's put some numbers onto it. So let's make this 3 amperes, 2 meters, and a magnetic field of 4 Tesla. I know the force is a vector. I got 2 pieces to it: magnitude and direction. My current here, my wire, is perpendicular to the magnetic field, so my cross product is just, the magnitude is just going to be ILD. And so this becomes 3 amperes times 2 meters times 4 Tesla, which is 24 ampere meter Teslas, which is just 24 newtons. Kyle, you've got the worst angle. You need to read out any of it to you?
The second to last one.
This right here. So we have F equals ILB, which is 3 amperes. Now I'm just plugging in the numbers.
Okay.
3 amperes times 2 meters times 4 Tesla. So we get 24 ampere meter Teslas, or 24 newtons. Or for those who are just feeling like it, 24 Newton radians. For no particular reason. You're looking at me like, how dare I? The second piece, the direction. What is the direction of the force on that wire? I would like each of you to have an answer in mind, and then we'll get everyone to actually voice an opinion. The direction of the force on that wire from that magnetic field. Magnetic field's coming out of the board, the current's flowing to the right. Have I done the hand ballet story? This is, on this test a couple of years ago, I had too many, like the tests were way too long. I had a whole bunch of, this situation, which way is the force acting on it, and to do that, a lot of right-hand rules, and so as people were all at the beginning of the test, they were all doing this right here. I wish I filmed it and then set it to music. It was actually sort of beautiful, but. All right, so, my choices are, now let's set up a coordinate system here. I, J, and then of course K coming out of the board. And so my choices are I hat, J hat, K hat, negative I hat, negative J hat, negative K hat. So there's 6 possible answers. Who says it's going to be enforced to the right in the I hat direction? Who says being forced upwards? Being forced out. Being forced in the negative I hat direction. Being forced down. And that means no one says it's being forced into the board. Hey, democracy works. It's being forced downwards. L, my L cross B here, L is in the direction of current flow. So L cross B, some points down. The cross product is down. Now I will say that when I first learned this in high school, decades later, I was working with some students at CPCC, and they were asking about direction of the force. I did not use this right hand rule. I had a different way of doing it. It works. But for those of you who, there's that debate over, do I show you all sorts of methods and you pick the one that you like, or do I stick with just one? And again, it's that situation where different students latch on to different techniques. The other way of looking at this is the current's flowing this way. It is creating its own magnetic field. The magnetic field created by this wire is out on top, in on the bottom. Out on top, in on the bottom. So I got 2 magnetic fields. I got this external 4 Tesla magnetic field, and then I have a magnetic field created by this current itself. Above it, I have a strengthening of my magnetic field. Below it, I have a weakening of the magnetic field. The wire will be forced towards the weaker magnetic field. The wire is forced downwards. Just another way. That's the way that I actually remembered over the course of decades. Generally not in textbooks, but that's just the way my mind worked at that time. Or the stem gun. I got current flowing that way. Current flows in the direction of positive flow. My magnetic field is out. The force on the charges is down. Okay, we got loads of time. Questions to here? I have current flowing down. I have 2 parallel wires. Current both flowing down. Each wire is creating a magnetic field. So let's color code. We'll make the one on the left blue. Call that I1 and call this one I2. And we'll make the distance between them something clever like d. So first off, what is the magnetic field? What is the direction of the magnetic field created by wire 1 at the location of wire 2? Direction of the magnetic field created by I1 here. Yes, by the way. Sorry. Precious, you were about to say something?
No.
My current's flowing down like that, into the board here, out of the board over here. So in blue, into the board, out of the board. It gets weaker as we go out. So I have a current that's flowing down on this wire right here, and my magnetic field's coming out of the board. Which way will this wire be forced?
Can you repeat the question?
Okay, so wire 1, or current 1 is creating a magnetic field out of the board over here. But I have a current flowing through this second wire, going down, in a magnetic field. So which way will this wire be forced because of this magnetic field created by this current?
Towards I1.
Because I have the current flowing down that way, my magnetic field is coming out of the board, thumb points in the direction of the force. So it will be forced towards it. Well, wire 2 is creating a magnetic field also. Which way is the magnetic field acting on wire 1? Sorry, trying to reword that. I2 creates a magnetic field. What is the direction of the magnetic field? Here, because of current 2.
Into the board.
Okay? That way, into the board, out of the board over here. And so it creates a magnetic field into the board, and then out of the board. Alright. Oh, wait, no, I drew that wrong. And then out. What is the direction of the force on wire 1 because of the magnetic field created by wire 2?
Towards I2.
Couple of side notes here. Number 1, they both are moving towards the weaker magnetic field because then in between the magnetic fields are in opposite directions, they're canceling out, it weakens. Number 2, they better be in opposite directions. Newton's third law of motion. Those are the equal but opposite forces. If they were in the same direction, that means I could take 2 wires, run a current through them, and then I could get them to move. Now, no class is complete. No life is complete without the math. So let's do some math here. So my strength of my magnetic field here, let's assume infinitely long wires for right now. So B is equal to mu naught I over 2 pi D. That's the strength of the magnetic field at this point right here from wire 1. The force on wire 2, the force on 2 from 1, is going to be equal to ILB. I sort of dropped the cross product there because the current is perpendicular to the magnetic field. And so this would be I2, oops, that's I1 up there. I2 times L times U naught I1. 2 pi d. Oops, lost a subscript, that's I1. And so mathematically, what is L in this case?
Is that the, length that it's moved that way? Is it the distance that it's moved that way?
No.
Like,
The length of the source.
Slightly more than that. You're almost there.
The length of the source, I think, starting before is not two. The length of the wire.
You're still dancing around it. Maybe you have the right answer again, it's just coming out a little bit off. In our nice ideal world, length of wire 1 and 2, which are parallel. So typically, if they're infinitely long, ultimately it's going to be an infinitely large force. So typically in a problem, you might have something like one wire like this and another wire like that. So they're actually only parallel for a short amount of time. So typically this equation is expressed as force per unit length, which becomes mu naught I1, I2 over 2 pi times the distance between them. And that is a 2 and not a backwards S. And so the force per unit length. And we can do this. We've got the time. Gone. That one's gone. Questions here before I'm going to set up for a demonstration. So while I'm setting up, we'll take a little break. But any questions before we have a little break and I set up for the demonstration? All right, let's take a small little break here while I set up.